Why 300 Hz exists and what it means. 300 Hz, 500 Hz. Some companies are even prototyping displays at 1000 Hz. If you think this sounds excessive, you are not alone. Most people cannot tell the difference between 240 Hz and 360 Hz in a blind test. So why do these ultra-high refresh rate monitors exist, and what technology makes them possible? The answer starts with competitive esports. Professional players in games like Counter-Strike, Valorant, and Apex Legends operate at the absolute edge of human reaction time. At this level, every millisecond counts. A monitor refreshing at 60 Hz updates the image every 16.7 milliseconds. At 144 Hz, that drops to 6.9 milliseconds. At 300 Hz, it is 3.3 milliseconds. At 500 Hz, just 2 milliseconds. These differences sound trivial, but in a fast-paced shooter where opponents move across your screen in fractions of a second, that extra clarity can be the difference between landing a headshot and missing entirely. High refresh rates also reduce something called motion blur. When you track a moving object on screen, your eyes are in a different position at the start of a frame compared to the end. This creates a smearing effect. The longer each frame is visible, the worse the blur. Doubling your refresh rate cuts motion blur in half. Going from 60 Hz to 300 Hz reduces blur by 80%. For competitive players, this means clearer target tracking and faster visual processing. But here is the uncomfortable truth. The jump from 60 Hz to 144 Hz is massive. Everyone notices it. The jump from 144 Hz to 240 Hz is noticeable if you look for it. The jump from 240 Hz to 360 Hz, most people struggle to see it. Beyond 300 Hz, you are chasing diminishing returns. Scientific studies suggest that human perception of motion plateaus somewhere around 300 to 500 Hz. Past that point, the improvements are more about measurements than real-world experience. So why do manufacturers keep pushing higher? Because the technology unlocks other benefits. To hit 500 Hz, panel makers had to develop faster pixel response times, better motion handling, and lower input lag. These improvements trickle down to more affordable monitors. A 240 Hz monitor today performs better than a 240 Hz monitor from 3 years ago because the technology evolved to support the extreme high end. The race to 1000 Hz might seem pointless, but it drives innovation that benefits everyone. Panel types and pixel response times. Not all 300 Hz monitors are created equal. The type of panel inside the display determines how well it can actually deliver smooth motion. There are 3 main panel technologies fighting for dominance in the high refresh rate space, and each comes with serious trade-offs. TN panels, which stands for Twisted Pneumatic, were the original speed demons. For years, TN was the only panel type that could reliably hit 240 Hz and beyond. TN pixels respond incredibly fast, often under 1 millisecond gray to gray. This makes them ideal for competitive gaming where every frame needs to be crystal clear. The problem with TN is everything else. Viewing angles are terrible. If you look at the screen from anything other than dead center, colors shift and contrast drops off a cliff. Color accuracy is mediocre at best. TN panels look washed out compared to modern alternatives. Most professional gamers tolerate TN for the speed, but nobody actually likes the image quality. IPS panels, which stands for in-plane switching, used to be too slow for high refresh rates. Early IPS monitors had response times around 4 to 8 milliseconds, which caused noticeable ghosting at high speeds. Then panel manufacturers developed Fast IPS technology. By refining the liquid crystal structure and improving overdrive algorithms, Fast IPS can now hit 1 millisecond gray to gray response times. This unlocked IPS panels for 360 Hz and even 500 Hz displays. Fast IPS gives you excellent color accuracy, wide viewing angles, and competitive speed. It is the sweet spot for most gamers who want both performance and image quality. OLED panels are the newcomers to the high refresh rate game. OLED pixels emit their own light, so they do not rely on liquid crystals changing position. This gives OLED instant response times, often measured at 0.03 milliseconds gray to gray. Motion clarity on OLED is unmatched. Colors are vibrant. Contrast is infinite because true black pixels are completely off, and viewing angles are perfect. OLED sounds like the dream, but it has one massive flaw: burn-in. If static elements like health bars or mini-maps stay on screen for hundreds of hours, they can permanently damage the panel. OLED monitors now come with 480 Hz refresh rates, but you have to baby them to avoid long-term damage. Now let's talk about what gray to gray actually means. GTG measures how how long it takes a pixel to transition from one shade of gray to another, typically from 10% brightness to 90% brightness. A 1 millisecond GTG spec sounds great, but it only tells you pixel transition speed. It does not tell you about motion blur caused by sample and hold, which is how long each frame stays visible. That is where MPRT comes in. Moving picture response time measures perceived blur during motion. Even a monitor with 1 millisecond GTG can have 6 or 7 milliseconds MPRT at 144 Hz because each frame is visible for the full refresh cycle. Input lag and system latency. Refresh rate is only half the battle. Input lag is the other half, and most people confuse it with something completely different. Input lag is not the same as ping. Ping is network latency, the time it takes data to travel between your computer and the game server. Input lag is system latency, the time between when you click your mouse and when that action appears on your screen. Even in offline games with zero network delay, input lag exists. System latency breaks down into three main components. First is peripheral latency, the time your mouse or keyboard takes to register your input and send it to the computer. High-quality gaming mice with 1000 Hz polling rates have peripheral latency around 1 millisecond. Cheap mice can be 10 milliseconds or worse. Second is processing latency, which includes both the CPU calculating what should happen in the game and the GPU rendering the frame. This varies wildly depending on your hardware and game settings. Third is display latency, the time your monitor takes to receive the frame from the GPU and actually show it on screen. Add all three together and you get total system latency, also called click-to-photon latency. Here is why this matters for 300 Hz monitors. If your system latency is 50 milliseconds total, a faster refresh rate will not help much. The monitor is updating every 3 milliseconds at 300 Hz, but the frame it is showing is already 50 milliseconds old by the time it arrives. You are displaying stale information faster, which does not solve the real problem. To truly benefit from a 300 Hz monitor, you need to attack latency at every level. That means a high polling rate mouse, a powerful CPU and GPU combo that can push 300 frames per second consistently, and enabling latency reduction features in your graphics driver. At the absolute competitive level, players aim for sub 5 millisecond total system latency. This requires a beastly PC running games at low settings to maximize frame rate, a high-speed monitor with minimal processing delay, and software tools to synchronize everything. Most gamers sit somewhere between 20 and 40 milliseconds total latency, which is still good, but not esports tier. Anything above 50 milliseconds starts to feel noticeably sluggish in fast-paced games. Input lag also interacts with refresh rate in ways that are not obvious. At 60 Hz, the best case scenario is 16.7 milliseconds of display latency just from the refresh cycle. At 300 Hz, that drops to 3.3 milliseconds. But the GPU also needs time to render frames and queue them for display. If your GPU is maxed out at 100% usage, frames can sit in a render queue waiting to be displayed, adding 2 or 3 extra frames of latency. This is where technologies like NVIDIA Reflex and AMD Anti-Lag come into play, which we will cover next. NVIDIA Reflex and AMD Anti-Lag. NVIDIA Reflex and AMD Anti-Lag are latency reduction technologies built into graphics drivers. They both aim to solve the same problem, but they work in slightly different ways. The core issue is render queue buildup. When your GPU is working at maximum capacity, the CPU keeps feeding it frames to render. These frames pile up in a queue, and by the time a frame reaches your screen, it might be several frames old. This adds latency even if your frame rate is high. NVIDIA Reflex tackles this by coordinating the CPU and GPU to minimize the render queue. Instead of letting the CPU run ahead and stack up frames, Reflex keeps the CPU and GPU in sync. The CPU waits until the GPU is ready to start rendering the next frame before submitting it. This eliminates most of the queue and ensures the frame you see on screen is as fresh as possible. Reflex works on NVIDIA GeForce GTX 900 series and newer graphics cards. It requires game developers to integrate the Reflex SDK into their games, so it only works in supported titles. As of 2025, over 100 games support Reflex, including Valorant, Apex Legends, Fortnite, Call of Duty, and Counter-Strike 2. The impact is significant. In some games, Reflex can reduce system latency by 30 to 50%. For example, in a game running at 200 frames per second without Reflex, you might have 40 milliseconds of latency. Enable Reflex, and that drops to 25 milliseconds. The difference is immediately noticeable. Your crosshair tracks targets more tightly. Your shots register faster. Everything feels more connected. Reflex also includes a low latency boost mode that disables power-saving features on your GPU, keeping clock speeds maxed out even during CPU-bound scenarios. This increases power draw, but further reduces latency. AMD Anti-Lag works similarly similarly, but uses a different approach. Instead of requiring game integration, anti-lag can be enabled globally through the AMD driver for any DirectX 9, 11, or 12 game. It dynamically adjusts frame pacing to reduce the time frames spent waiting in the render queue. AMD also released Anti-Lag Plus, which offers even better latency reduction, but requires developer integration, like Reflex. The downside is that Anti-Lag Plus had some early issues causing bans in competitive games because of how it hooked into game code. AMD has since fixed this, but it created trust issues. When directly compared, NVIDIA Reflex tends to deliver slightly better latency reduction than AMD Anti-Lag, especially in games with native support. The gap is not enormous, maybe 2 to 5 milliseconds in most titles, but at the competitive level, every millisecond counts. Both technologies are essential if you want to maximize the benefits of a 300 Hz or higher monitor. Without latency reduction, you are just displaying old frames faster, which defeats the purpose of ultra-high refresh rates. Frame generation technologies. Frame generation is one of the most controversial innovations in gaming right now. NVIDIA pioneered it with DLSS 3, and AMD followed with FSR 3 and fluid motion frames. The concept sounds almost too good to be true. Your graphics card generates entirely new frames using AI, inserting them between real rendered frames to double or even triple your displayed frame rate. A game running at 120 frames per second can look and feel like 240 frames per second or higher, with frame generation enabled. Here's how it works. NVIDIA DLSS 3. Frame generation uses motion vectors and an optical flow accelerator built into RTX 40 series GPUs. Motion vectors track where objects are moving in 3D space, but they only work for geometry. Shadows, reflections, particles, and other non-geometric elements need optical flow, which tracks pixel movement frame to frame. DLSS 3 combines both data sources plus color and depth information to generate a completely new frame that sits between two real frames. The AI essentially predicts what the scene should look like halfway through the transition and fabricates that image. When done well, the generated frame is nearly indistinguishable from a real one. AMD FSR 3 takes a similar approach, but without requiring dedicated hardware. FSR 3 with fluid motion frames works on a wider range of graphics cards, including older AMD and NVIDIA GPUs. The quality is not quite as refined as DLSS 3 because it lacks the optical flow accelerator, but it still delivers impressive results. AMD also offers a driver-level version called AFMF that works with any DirectX 11 or 12 game, even without developer support. This flexibility is appealing, though the image quality and stability suffer compared to game-integrated FSR 3. The catch with all frame generation is latency. Generated frames do not reduce input lag because they are created after your input has already been processed. If you click your mouse, the game engine calculates the result. The GPU renders a real frame, then frame generation creates an interpolated frame based on that real frame. The interpolated frame arrives one frame late by definition. This adds latency, typically around 10 to 20 milliseconds depending on your base frame rate. That is why frame generation must be paired with latency reduction tools like NVIDIA Reflex or AMD Anti-Lag. Without those, the added smoothness comes at the cost of responsiveness, which defeats the purpose in competitive games. Frame generation shines in single-player games where visual fluidity matters more than instant response. Games like Cyberpunk 2077, Horizon Forbidden West, or Microsoft Flight Simulator benefit enormously from frame generation. You get cinematic smoothness even on mid-range hardware, but in competitive multiplayer shooters, the latency trade-off makes frame generation controversial. Some pros swear by it, others refuse to use it. The consensus seems to be that frame generation works well if your base frame rate is already high, say 150 frames per second or more, because the added latency becomes less noticeable. G-Sync, Pulsar, and the future of motion clarity. The holy grail of display technology has always been eliminating motion blur without sacrificing smoothness. For years, gamers faced a difficult choice. You could enable variable refresh rate technologies like G-Sync or FreeSync for smooth tear-free gameplay, or you could enable motion blur reduction through backlight strobing for crystal clear motion, but you could not have both at the same time. Backlight strobing and variable refresh rate were mutually exclusive. until G-Sync Pulsar. G-Sync Pulsar is NVIDIA's solution to this decade-old problem. Announced in early 2024, Pulsar combines variable refresh rate with backlight strobing through a technique called variable frequency strobing. Traditional backlight strobing flashes the backlight at a fixed frequency, which works great at locked frame rates but causes flickering and image artifacts when frame rates fluctuate. Pulsar dynamically adjusts the strobing pattern to match the current refresh rate in real time. The result is motion clarity, equivalent to a 1000 Hz display on a 360 Hz panel, without the flickering or double image problems that plagued earlier attempts. The technology relies on two key innovations. First is adaptive overdrive, which adjusts pixel transition speeds based on both screen location and current refresh rate. Pixels in different parts of the screen can behave differently, so Pulsar compensates for these variations to maintain consistent clarity everywhere. Second is pulse modulation, which intelligently controls the brightness and duration of each backlight pulse. By synchronizing the backlight flash with the exact moment pixels finish transitioning, Pulsar eliminates the blur caused by sample and hold displays while keeping the image comfortable to view. G-Sync Pulsar monitors require a brand new G-Sync module with custom hardware to handle the adaptive strobing algorithms. This means older monitors, even those with existing G-Sync Ultimate chips, cannot be upgraded to support Pulsar. It also means Pulsar monitors carry a premium price tag compared to standard high refresh rate displays. Asus announced the first G-Sync Pulsar monitor, the ROG Swift PG27AQNR, as a 27-inch 1440p display running at 360 Hz, though availability has been limited since its announcement. Looking further ahead, prototypes exist for 500 Hz and even 1000 Hz displays. Some companies are experimenting with dual-mode monitors that can switch between 1440p at 500 Hz and 720p at 1000 Hz. The idea is that competitive players could drop resolution for maximum speed when playing fast-paced shooters. Eye tracking technology is also being explored for foveated refresh rates, where the center of your vision gets the full 1000 Hz, while peripheral areas run at lower rates to save processing power. For most people building or upgrading a PC in 2026 and beyond, a 360 Hz monitor with modern features like fast IPS panels and low input lag represents the sweet spot. You get competitive level performance without chasing extreme diminishing returns. But the race to 1000 Hz and technologies like G-Sync Pulsar prove that innovation is far from over. Check the next video for more tech breakdowns that actually make sense.